Hello, BC Calculus students. This is Mr. Johnson, and we're going to continue in section 8.6. We're going to talk about differentiation and integration of power series. And so this gets a little bit complex, but we'll just work through some examples. I think you'll start to see some patterns, and hopefully with some practice, it will become more comfortable. So first, there are some definitions here. I think it's important to know that there's not necessarily a definitive approach, I guess is what I could say. Sometimes, I think what you want maybe is a formula to use of sorts, and there really isn't a formula. You have to be creative with this, and there isn't necessarily a one-size-fits-all type of approach to differentiation and integration of power series. Hopefully, with some examples here in the notes, you'll start to see the patterns that form and some of the strategies. But when we look at the definition here in the theorem, there's a couple really important points that I think to make, and that is that number one, we want to continue to compare our power series right now to the only one that we know, and that single important power series is 1 over 1 minus x, which is 1 plus x squared plus x cubed, and so on out to the general term and beyond. Now, again, I told you have to memorize this one, and this is the one we're trying to compare everything to in some way or another. So basically, there are three approaches. Number one, you want to algebraically manipulate the unknown so that it fits this model. That's what we did in examples 1 through 3. Number two, you want to differentiate something to fit the model. I'm going to show you that here in the next couple. And then number three, you may have to integrate something to fit what you want to fit. Now, when you do that, the radius doesn't change. So if I was to differentiate something in order to fit the model of the only power series that we know, or if I was to integrate something, the radius is still consistent, but the ends of the interval could either both close or one close, or they could both stay open. So if you noticed in the other examples, we didn't consider the endpoints. We didn't need to consider the endpoints because as we algebraically manipulated the series, we were able to come up with a model based on our parent function here, our parent power series, and we didn't have to worry about the endpoints. We just had to worry about what we substituted and whether that changed the interval itself. In the cases that we're going to see here, either by differentiation or integration, we will not have a difference in radius. However, we may have a difference in what the endpoints do, and I'll show you that in a minute as well. Another thing I want to mention is that as you look at the formulas, you can see like the n equal to 1 and the n equal to 0 stuff. That actually is not necessarily consistent. You can come up with a variety of formulas that could still generate the power series, and they don't necessarily, for example, if you take the derivative, it doesn't need to start at 1. I mean, you could come up with a variety of representations that would be accurate. Maybe it would start at 0 or 2 or something like that. So don't be too caught up with having to start at a certain spot, because really this generator is intended to generate the actual series that you came up with. And so all you need to make sure is that whatever formula you come up with, it must accurately generate what you just found. Okay, and so don't be too caught up with how n begins. Don't be thrown off by saying, well, this is n is 1 and this is an n is 0. There's not a whole lot there that you have to be worried about right now. That's just part of the definition as we can see it. Okay, so let's try example 4. This is a function I don't remember from physics when I took it in high school. Maybe some of you have seen it, but the bottom line is that it's a series that we're going to take the derivative of. And my goal here is to show you that it's actually pretty simple. I have seen problems that are like this, where the problem is really ugly looking, and they say, what is the derivative? And it's actually a really easy process. They're trying to kind of throw you off, I think, by saying that. Keep in mind that everything I'm highlighting right now is simply a number. It's a coefficient. It's not a variable. It's just simply some number. I don't know what it is. So when you take the derivative of a variable that's a power rule, which this is, because keep in mind that x to the 2n, that's just a simple power rule, and the derivative of something like that is that you bring the power down. So I'm actually going to write this out really quickly. So if we're taking the derivative with respect to x of x to the 2n, where n is some number, I get 2n times x to the 2n minus 1. That's the power rule of differentiation. That was the first derivative you learned last year. We're going to do the same thing, but keep in mind that this must be multiplied by all of this stuff, because all of that stuff I just circled is just simply a number. So what is the derivative of this ugly looking function? Well, the derivative would be, let's see, negative 1 to the n divided by 2 to the 2n times n factorial squared. None of that changes at all. It's just simply a coefficient that comes along for the ride. However, because of the power rule, I have to bring my 2n down, and I have to decrease my power by 1, and I'm done. There's my derivative. So it looks really ugly. It is simply a power rule. Okay, let's go on to the next example. All right, we're going to look at example 5, and we're going to start digging into this slightly more complex stuff where we're looking specifically for a power series for this particular rational function here, and we're looking for what we could possibly derive to get there. So I'm just going to walk you through what I would do, and that is that you're just trying to brainstorm something similar to the parent power series that we have that we would derive. Now let's just kind of jump into it. If we were to take the derivative of the series that we know, keep in mind that that's the same thing as 1 minus x to the negative first. So if we were to take the power rule here, we'd bring the power down, we would decrease the power by 1, we'd multiply by negative 1 because of the chain rule, because remember on the inside the derivative is negative 1. And then what we get is 1 minus x to the negative second, and believe it or not, it is exactly what we're looking for. So notice that if you were to take the derivative of the only power series we know, we end up getting the same exact thing we're looking for. Okay, so what does that mean? Well, let's start with the power series that we know, which is 1 over 1 minus x. And I know, I'm going to leave a little bit of extra space here, I think. So I know that this is 1 plus x squared plus x cubed and so on, out to my general term and beyond. Okay, I'm going to take the derivative of both sides. So I'm taking the derivative of the left, I'm taking the derivative of the right. So the derivative of the left, I just showed you, is exactly what we're looking for. It's 1 over the quantity 1 minus x squared. The derivative for the right, I'm just going to derive every single part. So the derivative of 1 is 0, the derivative of x is 1, the derivative of x squared is 2x, the derivative of x cubed is 3x squared, and so on. The general term would have a derivative of n times x to the n minus 1, and I would continue. That's it. This is a power series representation using the only series that you have currently memorized, the parent power series, and all we had to simply do was take the derivative of the only thing we know. It happens to be what we were looking for here, and we just have to derive every single part of that particular power series. Now let's tackle the interval of convergence. Now remember what I said, the radius doesn't change. So the radius of the original is 1, because remember the interval is from negative 1 to 1. So the radius of convergence is 1. So the radius doesn't change here. We're looking for the same basic interval. So in other words, the initial interval would be the same as what we started with that parent power series. What we have to figure out is, by deriving this, did we change the endpoints? So for example, if x is equal to negative 1, and I'm looking specifically at my general term here. Okay, I'm looking at what does the general term do. So I have this the series n times x, which is -1 to the n minus 1. And the question becomes what we did in the first half of chapter 8, is this convergent or divergent and why? Well, this alternates. However, the limit of the non-alternating terms as n goes to infinity is infinite. So it alternates, however, the limit of the terms that don't alternate is infinite. Therefore, this is divergent. If we were to take a look when x is equal to 1, that's even easier because now it's simply just n times, if x is 1, it's n times 1. This, by the nth term test, is also divergent. We don't have to worry about an alternator. So in other words, the interval of convergence is exactly the same. It didn't end up changing at all. It's just simply from -1 to 1. Okay, so there's your first example. Finding power series by differentiation. Let's take a look at number 6. Example 6. We're finding the power series representation for inverse tangent or arctangent. Now this time I'm going to go ahead and do integration. And the reason for that, if you think back on what we know about inverse tangent or arctangent, is that the antiderivative of 1 divided by 1 plus x squared is equal to arctangent. That's just one of the ones we had to memorize last year. That's one of the ones you need to know this year. Hopefully that's in your memory. Again, can you do that right now for this problem? Probably not at all, because this is really new and is pretty abstract. But again, that statement in red that I just wrote, aside from anything in chapter 8, you have to know that statement. You have to know the antiderivative of 1 over 1 plus x squared. Anyway, so what we have here is a situation where we have some sort of representation connected to this right. Oops, sorry. This right here is connected to 1 over 1 minus x, the only power series we know. Because if you look back on example 1, you can take a minute to do that. In example 1, so example number 1, we figured out that 1 over 1 plus x squared was equal to 1 minus, actually, you know what, I'm going to leave a little bit more space here, was equal to 1 minus x squared plus x to the 4th minus x to the 6th. We let the general term be written as -1 to the n times x to the 2n, and then we continued. Okay, so we found that in example 1 connected to the series 1 over 1 minus x. So what we're going to do with this is we're going to integrate both sides. And on the left side, when I integrate that, I'm going to simply get inverse tangent, which is exactly what I'm searching for. Okay. On the right side, I have to take the antiderivative of every part. So the antiderivative of 1 is x. The antiderivative of x squared is going to be x cubed over 3. The antiderivative of x to the 4th is x to the 5th over 5. X to the 7th over 7. And so on. I'll make the general term x to the 2n plus 1 divided by 2n plus 1, and we would continue this pattern. Now, not to cause further trauma, but remember, you do have to add a c as we take antiderivatives. Now, is there a c on the left side as well? Sure, but let's just group it all together. Let's just say we have a plus c on both. We'll just group them over to the right. We'll just call it a single plus c. Okay, if you really felt inclined, you could put a plus c sub 1 on the left, plus c sub 2 on the right. You could combine them somehow, subtraction on one side of them, and then just make it a c. Okay, so you have some sort of constant associated with this problem. Now, we need to figure out what the constant is. We gotta somehow analyze that. And the way we're going to do that is we're going to let x equal some numeric value. You could let x be 7, 12, 85, -4. It doesn't matter. You could let x be anything. And technically, you should be able to figure out the c. The problem is that everything over here is infinite, which means that if you pick a silly x value, you're going to be adding it forever. So let's pick a value that you can actually calculate forever. And that value would be 0, because every single one of these terms right here, every single one of them has an x in it, which means that if x is 0, you know that all of these cancel, and you're simply left with c on the on the right side of the equation. Now, the question becomes, for some of you this is easier than others, what is inverse tan of 0? And hopefully you know the answer is 0, which means that c is simply 0. Now, that's pretty unsatisfying because you had to go through all the trouble of analyzing what c was. I'd say 9 times out of 10, c is 0, but you'll have that problem where c is something different. And you got to know that. And it doesn't matter if it's a free response question, you have to show analysis of c. Okay, so what we have, and again, the question asks for the power series for inverse tangent, and I think we finally have it. So it's going to be x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7 over 7. And we will continue to the general term, and then we'll continue beyond that. Okay, let's analyze the interval of convergence. Now remember, we're dealing with the same kind of thing, if you go back to example 1 for a minute, the interval for 1 over 1 plus x squared is -1 to 1. So it's going to be a similar interval. We just don't know if either or both or neither are closed. We just got to figure that out. So let's go ahead and let x equal -1. And again, we're going to look at the general term. So I'm focused on this general term. What if x is -1? My series then would be -1 to the n times -1 to the 2n plus 1 divided by 2n plus 1. Now, we talked about this a lot in the earlier part of chapter 8, but 2n plus 1 is always odd, which means that -1 to the odd number is always -1. So what you have in the numerator is -1 to the n times -1, which means that you have -1 to the n plus 1. Sorry, let me write this summation here. So in the numerator, you have -1 to the n plus 1 over 2n plus 1. And the question is this alternate, or excuse me, is it convergent or divergent? And, think back to all the 10 tests that we studied. This is convergent by the alternating series test. I'll kind of speed through that. But basically, number 1, is it alternating? Yes. Number 2, it is, without the alternator, is it decreasing? Yes. And number 3, as n goes to infinity, is the limit 0? Yes. So this is convergent. Okay, we have if x is 1, we have -1 to the n times 1 to the 2n plus 1 over 2n plus 1. Okay, well the 1 to the 2n plus 1 is, of course, just 1. So what we have in the numerator is -1 to the n and 2n plus 1. This is basically the exact same conclusion. So it's convergent as well by the alternating series test. Okay, so what this means is that the interval of convergence for this is -1 and to 1, and we include both of these endpoints. They're both convergent, so it's closed on both ends. Okay, let's go to the next page. All right, it's a little daunting, but we're going to try an entire FRQ now. And this is dating back a ways. This was 1982, so it was a long time ago. Most of the FRQs, not to overwhelm you or anything, but most of them we can't do right now. We don't have enough information. But this one we can do. This is everything that we've been studying so far. So we have the first four terms and a general term for the series expansion about x equal to 0. Remember, when it says about x equal to 0, that means centered at x is equal to 0. And by the way, remember how we have the only power series that we know. You're probably sick of me saying that, and you're probably sick of writing that. But this power series is centered at 0. Okay, so that's a good thing because that's the only one we can use right now. So it's centered at 0, and we're looking for f of x equal to natural log of 1 plus x. And our goal here is to somehow compare the only power series we know to the natural log of 1 plus x. So what I'm going to do is I'm going to take and look at what do I know about natural log, and what do I know about derivatives or integrals. And as you think through the possibilities in terms of manipulation, there's really nothing we can do directly to get there. I don't think, there's no algebraic manipulation we can do. So it's either going to be a derivative or an antiderivative to try to figure out how to compare these two. And so my conclusion that I come up with is that the natural log of 1 plus x is equal to the integral of 1 divided by 1 plus x dx. So we know the antiderivative of 1 over 1 plus x is the natural log of the absolute value of 1 plus x. And so therefore we're able to compare these through integration. Also, we're going to be able to figure out 1 over 1 plus x is a pretty easy comparison to 1 over 1 minus x. So that's how we're going to start first of all, is that we're going to look at 1 over 1 plus x, and we're going to simply take that and manipulate it just slightly like we did in some of the other problems to look just like the original, except just a little tweak to that sign. And so my series will be, actually, let's go ahead and move this a little bit here, just so we have some room to write around it. Okay, so we have 1 plus negative x plus negative x squared plus negative x cubed, and so on. My general term will be negative x to the n. I suppose I didn't need all that space yet. So this is going to be 1 minus x plus x squared minus x cubed, and then so on. Here's my alternator. Okay, that one's not too bad, I don't think. And so what we're going to do with this is take the integral of both sides. So we're going to integrate and integrate. And we know that the antiderivative of 1 over 1 plus x is going to be the natural log of 1 plus x. And then we're going to take the antiderivative of every part of this other of this polynomial. So we have the antiderivative of 1 is x, and the antiderivative of x is x squared over 2, and x cubed over 3, and x to the 4th over 4, and so on. The general term would be negative 1 to the n times x to the n plus 1 divided by n plus 1. Keep in mind that the general term can be represented a variety of ways. So for example, my general term would be accurate if x starts at 0, because if x starts at 0, my first term is x. For example, let's say, just for the sake of discussion, let's say that you wanted the general term to be negative 1 to the n plus 1, or n minus 1, it doesn't matter, and then x to the n over n. If n started at 1, then your first term is x. if n was 2, your next term is here, n is 3. So depending on what n starts with, your general term could be represented a variety of ways. But again, the problem says list the first 4 terms and the general term. And so for what it's worth, I'm going to go with these 5 items here. And you know what I shouldn't have done is I should not have, well, no, that's okay. I've written it okay. So there we go. So that's what I'm going to go with. Is I was going to say I should not have put an equals, but I did put a plus dot dot dot, and so therefore it wasn't an approximation. It is equal as long as it's under the interval of convergence. Okay, let's take a look at part B. All right, part B says for what values of x does the series converge? So we're having to analyze now what we're going to look at in terms of the interval. Now keep in mind that for the original that we started with, we have the absolute value, whoops. We have the absolute value of x is less than 1 in terms of the interval of convergence. And so we're really starting with, for the natural log of 1 plus x, we're starting with -1 to 1 with regard to the interval. So what we want to do is test both ends of this. So let's let x equal -1. Remember, we're testing our general term here. So we have the interval, sorry, we have the series -1 to the n times -1 to the n plus 1 divided by n plus 1. Let's see, let's simplify that down a little bit. So that's going to be -1 to the 2n plus 1 over n plus 1. Remember, 2n plus 1 is odd. So we actually get, and I'm going to do this like this. I'm going to take that -1 and I'm going to factor that out so that I simply get this. Okay? So in other words, the numerator is always -1. I don't want to worry about the -1 right now. I just want to look at what's happening to 1 over n plus 1. So this is not an alternator. It's just simply the series 1 over n plus 1. And if I take a look, for example, at the limit as n goes to infinity of 1 over n plus 1 divided by 1 over n, I get 1, which is greater than 0. And if you think back to all those tests we had, we could say that this is divergent by the limit comparison test. And the reason is that, I'm comparing it to the series 1 over n, and that diverges by the p-series test. So that's kind of a lengthy one. There's a couple ways we could probably do that, but there you go. That's one of them. Okay, so that's divergent, so we don't care too much about that in terms of the change. If x is 1, then I have a series, let's see, this is going to be -1 to the n. Notice if x is 1 to the n plus 1, that doesn't impact anything, so that's just going to be 1 divided by n plus 1, and this is convergent by the alternating series test. Okay, so our interval for part B is going to be -1 is less than x is less than or equal to 1. It's going to be our final interval for part B. Okay, let's take a look at part C. So for part C, we're looking at to estimate the error in evaluating natural log of 3/2 by using the first 5 non-zero terms. So this is the alternating series test error bound that we studied during that section of those alternating tests in section 8.3, I think it was. So we're looking at the natural log of 3/2, and keep in mind that if the natural log of 1 plus x is being used, that means that x is equal to 1/2 here, okay? But we do have to come up with the first 5 terms. We actually need the 6th one because we're using the error bound method. So let's go ahead and write out, because I didn't do that earlier. Let's take a look. We have x minus x squared over 2 plus x cubed over 3 minus x to the fourth over 4. The pattern obviously would continue x to the fifth over 5, and we should be able to end there at the sixth term. Keep in mind that we're using the first 5 for the estimation, but that sixth term, that's the key to the error-bound method. So when we're looking at the error-bound method, remember the error is equal to the absolute value of the actual, which is the natural log of 3/2, minus, I'm just going to call it p sub 5, because that's the polynomial to the fifth degree, which is this, in this case, the first 5 terms. And you have 1/2 as your x value. And we know it's less than or equal to the first discarded term, the absolute value of that, by the way. And I'll just make that 1. I don't have a calculator, and I don't know if this is calculator or not. So my maximum error here would be 1 divided by 2 to the 6th times 6. That would be the maximum error. So my error is less than or equal to that value based on the alternating series error-bound method. Okay, let's do the last part. We're almost done. So part D says, using the results from part A to determine the logarithmic function whose series is that particular one, which I'll just write out here. So we have -1 to the n plus 1 divided by 2n times x to the 2n. I'm going to list out a couple terms. I think this might help us. So if n is 1, then my first term will be positive x squared over 2. My next term, when n is 2, is going to be x to the fourth divided by 4. My next term is positive. That's going to be x to the sixth divided by 6, and x to the eighth divided by 8, and so on. Okay, now I'm just going to, instead of scrolling all the way up, I'm going to write out my original from part A. So my original from part A was x minus x squared over 2 plus x cubed over 3 minus x to the fourth over 4. So I have to try to think about how am I comparing these two. So in other words, how could I go from x and get x squared over 2? How could I go from x squared over 2 and get x to the fourth over 4? Notice the signs are the same, so I don't really care about that right now. I'm just trying to manipulate each of these in exactly the same way in order to get the stuff in red, which I'm trying to analyze. So what would I do to x to get x squared over 2? What would I do to x squared over 2 to get x to the fourth over 4, and so on? What are the patterns there? One of the things I'm seeing is that if I multiply by 1/2, then I end up getting the pattern in the denominator. So if I multiply by 1/2, I'll get the 1/2 here, the 1/4 there, I'll get the 1/6 here, the 1/8 there. The other thing is that if I was to substitute in x squared into everything in blue, then that would match up as well. So again, if I was to take, for example, and put in x squared for each one of these x's, if I was to substitute that, I would get x squared, I would get x squared squared, which is x to the fourth, I would get x squared cubed, which is x to the sixth, x squared to the fourth, which is x to the eighth. So I think this green would be connected directly to what we're analyzing in the red. Okay, now what does that mean? Well, remember the blue was connected to the natural log of 1 plus x. That means that the green is connected to 1/2 the natural log of 1 plus, remember I'm substituting in x squared for all my x's. And so my function that I'm analyzing, given that series that they give me in this part, is going to be 1/2 natural log of 1 plus x squared. Okay, so that's an entire FRQ. That is it for section 8.6. There's a lot more practice that we can now do together in 8.6. Thank you.